Guys, from today onwards, we are going to deal with respect to the haloarenes. Okay, so till the previous video we have seen the important properties, even we have seen certain important reactions, but all those were constrained or they were all related to that of your haloalkanes. But today onwards we are going to deal with the topic of your haloarenes. That means our halogen group will be attached to that of your aromatic compound. The basic aromatic compound which we all know is that of your benzene. So in this first we have to understand what is that. They say one important point over here, a very important point. So whenever we are seeing the reactivity of haloalkanes and haloarenes. Yes, the reactivity of your haloalkanes and haloarenes towards nucleophilic substitution reaction. Towards nucleophilic substitution reaction. What we are observing is that the reactivity of your haloalkanes is very much higher when compared to that of your haloarenes. Or in simple words, what we can say, the reactivity of haloarenes towards the nucleophilic substitution reaction is very less. So what they want to say, of course, whenever we are having this RX bond and when an incoming nucleophile, for example, an hydroxide ion, so what should happen? This X should move out and this OH should come and attack and you should get as an ROH. This case was simple whenever our R was a CH3 group. CH3X plus OH minus give rise to CH3OH. It would have been obtained at a simple conditions. But when we are taking the same R group as that of your benzene ring, remember, and when we are doing this reaction, that is a nucleophilic substitution reaction, what we are saying, in normal condition we are not getting our phenol. Only when we are making we are maintaining a drastic conditions, that is a very high temperature, very high atmospheric pressure, then only we can see or we can obtain what? Our nucleophilic substituted product. Of course, now the question arises within us, why is it so? Why does your haloalkenes are having the higher reactivity towards the nucleophilic substitution reaction, or why does our haloarenes is having the less reactivity towards the nucleophilic substitution reaction? So in order to understand that, first of all we have to understand what are the basic things needed in a molecule or in a compound so that it can undergo nucleophilic substitution reaction. Alva, we know that if a nucleophilic substitution reaction has to take place, what should happen? The RX bond should break easily. That is the first thing. Alva, if the RX bond is breaking easily, what happens? Easily a carbocation will be formed. Once we are having a positive charged species, easily an incoming negatively charged species can attack it. So this is something we have to understand. When the reactivity is more, what is it simplifies? There is a little amount of energy is maybe needed to break this bond. But when it is requiring a higher reactivity, that means what? It requires a very high amount of energy. Reactivity kammi untu andre artha enu? That is not easily reacting. Why it is not easily reacting? Because in order to break this bond, we require an enormous amount of energy. So this is the hint what our detectives are having. That is you. So this is the main hint. Now we have to break this hint that why such bond is existing, or what is the reason for the supplying of the high energy is required in case of your haloarenes. So basically all those properties what we are going to study is mainly categorized under 4 different properties. Okay. First and the foremost thing is that of your resonance effect. Resonance effect. So of course when I am seeing, for example, if I am going to take as a chlorobenzene as my haloarene. So what happens over here? This chlorine will be having the lone pair of electrons with it. So it will try to interact this lone pair of electrons with the pi rings of the benzene. So what happens when we are seeing these resonance structures, you can just notice over here. This indicates your resonance arrow. See, this lone pair of electron is given over here. Again, I do here now electron density increases. Alva. ಎಷ್ಟು ಬಾಂಡ್ ಆಗುತ್ತೆ 1 2 3 4 5. So it will be pentavalent, unstable. So now this will be moving over to this carbon. See, you can see how I am writing. So ಯಾವ ತರ structure ಬರುತ್ತೆ ಈಗ? So here you will be getting as what? Double bond Cl. Yes. Here you are having the negative part, which has been come over here like this. Then as it is. Now what happens? This negative will be given over here, whereas this pi bond electron density will be carried by this carbon. So how will you write it? Yes. Double bond Cl. Here I am having the bond. Here I am having the negative sign. And here I am having one more bond. So once again, if I am going to write, what happens? Now this will be gone over here. This will be coming over here. So now you will be having here and here negative sign, double bond Cl. Then afterwards, the final structure, how can I write? Yes, now this can come over here. This can go over here. So I would be getting as what? Yeah, can you see now? Here I am having the bond. Here I am having a bond. Here I am having a bond. Single bond Cl. So if I am going to write its hybrid structure, overall structure of this canonical structures, how can I write it? Overall structure can be written in this way. This rotating, the pi bond is rotating, and wherever we have seen that negative marks, this electron rich density here, here, and here. Simple words in ortho and the para position. But when we are observing this canonical structures or that of your resonance structures, what we are observing in your structure of second, third, and that of your fourth, we could see that there is a double bond character between your C and the Cl. I repeat, so when we are observing the resonance structures in the structure of second, third, and fourth, what we are observing is there is a double bond character between your CX bond. Alva. So we know that whenever a single bond is there, we require less energy. But whenever the double bond exists, we require somewhat more energy. And whenever the triple bond exists, we require more energy. Why is it so? What is happening over here? As the bond order is increasing, what happens to the bond length? It decreases. When the bond length is decreasing, what happens? The stiffness increases. So in order to break that bond, we require the higher energy. So that is the reason we can give as a one important reason through the resonance effect that why does your haloarenes are having the less reactivity towards the nucleophilic substitution reaction. It is mainly because in the resonance structures we could observe that your CX bond is having a partial double bond character. And due to that double bond character, we require a high energy to break that bond. Is that clear? That is the reason when a haloalkane can give a nucleophilic substitution reaction products at the room temperature, but the same haloarene part cannot undergo the nucleophilic substitution reaction at room temperature. Why? Because the room temperature is not enough to break this CCl double bond. This is through your resonance effect. But it doesn't stop over here. One more explanation is there. That is with respect to that of your hybridization. Hybridization of carbon atom. Hybridization of our carbon atom. So what does it say? So when I am talking about a CH3X bond, that is how the product will, your structure will be CH3 and then X. So when I am considering the hybridization of this carbon, remember it is an sp3 hybridized carbon atom. What it is? In a haloalkanes, the hybridization of your carbon is sp3 hybridized. But when I am taking the case of your haloarenes, for example your chlorobenzene, here whatever the C bond is there, it is an sp2 hybridized carbon atom. I repeat, in your haloarene, the hybridization of the carbon atom is sp2 hybridized. So what happens over here? So when it is sp3 hybridized, whatever the CX bond length is there, alva, it is nearly in the order of we can say 179 picometer. 177 to 179. Yeah. But when you are considering the CCl bond in a haloarene, you can just see it is having the range of 169 picometer. 169 picometer. As I mentioned earlier, what is that? As the bond length decreases, the energy required to bond breaking will be increasing. The same scenario is happening over here. In the haloalkanes, since the carbon atom is sp3 hybridized, its bond length is somewhat more. So it is very easy to break. But when we are comparing it with respect to the haloarenes, you can just see, since the carbon atom is sp2 hybridized, it will be firmly held to that of your CX bond. So in order to break that bond, a higher amount of energy is required. So this is another important point which is to know that why does your haloarenes is not having the higher reactivity towards your nucleophilic substitution reaction. Coming to the third point. Of course, when we were dealing with the SN1 mechanism, for respect to that of your haloalkanes, CH3, 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 since here was X. So first step in the SN1 mechanism was what? Is the formation of your carbocation. So it was forming this carbocation. And when I said that this was the slowest step, why did I mention it? Because whatever the product we are getting over here in the first step, it is a tertiary carbocation, which is highly stable. This was in the case of what in your haloalkanes. But when the same scenario is studied under your haloarenes, what happens over there? This also undergoes the ionization, but when it ionizes, what I am going to get, that is very much important. So this is called as what? Phenyl cation. Phenyl cation. And when we are studying its stability, remember, it is highly unstable. It is highly unstable. So when such a plus itself is not existing in the system, how can an OH minus come and sit? Alva. So that is the reason. It could be one more important reason which we are studying under the concept. It is called as instability. Instability of the phenyl cation. Instability of the phenyl cation. Since the formed phenyl cation in the process is highly unstable, it is not promoting the nucleophilic substitution reaction. An important thing you should also remember, when such system is not, your phenyl cation is not able to form, what we can say, your haloarenes cannot undergo substitution reaction, cannot undergo substitution reaction through SN1 mechanism. Alva. Because in SN1 the major thing was what? Is the formation of the carbocation. But we are seeing that what? Whenever a haloarene is forming a carbocation, is highly unstable. And in chemistry, the instability is not favoring anything. It should be a stable. Then only we can proceed the reaction. So what happens? Due to its instability, it cannot form the carbocation, and that is the reason what we can say, haloarenes can't undergo the substitution reaction through the SN1 mechanism. So what we have learned, first and the foremost thing, through the resonance effect, we came to know that your CCl bond is a double bond character. So in order to break that bond, a higher amount of energy is required. Second, we learned about the hybridization of the carbon atom. So when you are considering your haloalkane, it is an sp3 hybridized carbon atom having the CX bond length of nearly 177 picometer. But when you are considering the haloarenes CX bond, it is nearly in the range of 169 picometer. So in order to break the CCl bond in a haloarenes, an enormous amount of energy is required. So that is the reason drastic conditions has to be maintained for a nucleophilic substitution reaction. And in third part we came to know is with respect to the instability of the phenyl cation. So whenever a nucleophile should come and attack, means the carbon atom should bear a positive charge. When such a positive charge it has to be bared, so such an intermediate should be highly stable. But in the case of an haloarenes, what we are seeing, the formed phenyl cation is highly unstable. So that is the reason it will not be going to exist in the system. When such a positive thing is not there on the carbon atom, of course the nucleophile can't come and attack your haloarenes. Coming to the fourth point. Hope you can only explain it. What is that? High charge density on the benzene. High electron charge density on the benzene. Alva. So of course what we know, whenever we are seeing the structure of the benzene, how we are going to write it? It is in this way. Or similarly we can also write it in this way. That means what? Delocalization of the pi electrons. What does it mean? That is, this pi electrons are in a continuous motion. So of course what happens, since pi means what? It is also an electron. And when a nucleophile is coming and attacking, what is the charge on the nucleophile? It is also negative. What is the charge on the electron? It is also negative. So what happens? Electron-electron repulsion takes place. Able to understand? So due to the high charge electron density on the benzene ring, it is also not favoring the formation of a nucleophile substituted product. Are you able to understand, guys? So these are the important 4 points which can be said as an evidence to say that why does your haloarenes are least reactive. I repeat, why does your haloarenes are least reactive towards the nucleophilic substitution reaction when compared to that of your haloalkanes. So in case if you have been given with a question, arrange the following in the increasing order of reactivity, in the increasing order of reactivity towards nucleophilic substitution reaction, and you have been given with, I'm just going to give you 2 important part. One is your haloalkane and that of your haloarene. Can you please arrange it? What is the question? They have said arrange the following in the increasing order. That is at the last I should get what? Increased reactivity compound. In the reactivity towards your nucleophilic substitution reaction. Of course, we came to know from this points, what is that? Of course, your haloalkanes will be having the higher reactivity towards your nucleophilic substitution reaction when compared to that of your haloarenes. So, yaad first barutte, of course, first will be your Cl, which will be very much least reactive, alva. Benzene ringiಗೆ Cl attach ಆಗಿರುತ್ತೆ, it will be in haloarene. So, it will be very least when compared to that of your methyl chloride. Are you able to understand why haloarenes are having least reactive? Of course, we saw. So when we are seeing the resonance effect, we are seeing that your CCl bond in a haloarene is having a double bond character. So in order to break this bond, an enormous amount of energy is required. So therefore, I am saying, what is that? Not possible antana helala. What, you can make my voice clearly? What I am saying, nucleophilic substitution reaction towards the haloarenes is difficult. But I am not saying it is not possible. Of course it is possible, but at a drastic conditions. That is at a higher temperature or the pressure. But when haloalkanes, it is not the case. Maintaining the normal temperature itself, we can do our nucleophilic substitution reaction. That is not a case. But in a haloarene, why we require such drastic condition? So we are seeing through the resonance effect, what is that? Your CCl bond is having a double bond character. So whatever the extra energy we are providing, alva, that energy will be utilized to break this bond so that an incoming nucleophile can come and sit to that carbon atom. Then also we saw with respect to the hybridization of the carbon atom, what is that? When we are talking about the haloarenes, the carbon atom hybridization in a haloarene is an sp2 hybridize. So whenever it is an sp2 hybridize, what happens? The bond length decreases. So when the bond length decreases, what happens? The energy required to break that bond, it increases. That is can be a second important point. Third most important point, what is that? Is the whatever the carbocation it is forming during the nucleophilic substitution reaction to the SN1 mechanism, it is highly unstable. Unstable means what will happen in that reaction mixture, it is not going to be existing at a longer period of time. Alva very short interval tanka matra irutte because of its unstable condition. So of course when it is not existing itself, what happens? The nucleophile cannot come and sit So the nucleophilic substitution reaction does not take place. Coming to the next part, that is your high electron charge density on the benzene. Of course, whenever we are writing the benzene, we know that it is with respect to the delocalization of the pi electron. Since the pi electrons are highly delocalized, what happens? All the time the benzene ring will be very rich in the electron density, that is nuclear charge. Sorry, negatively charged. Incoming your nucleophile is also a negatively charged species. Mutual repulsion takes place, so it will not be favorable to that of your nucleophilic substitution reaction. Okay. So next we are going to see how can we, of course I have mentioned you what, it is difficult, but it is not, we can't say it is not possible. Of course it is possible. So next we are going to understand what are the possibility we can conduct this nucleophilic substitution reaction, and how can we increase the reactivity. I repeat, how can one increase the reactivity of your haloarenes towards the nucleophilic substitution reaction. So guys, now let us see the reaction part of your haloarenes. That is reaction of chlorobenzene towards nucleophilic substitution reaction. Towards nucleophilic substitution reaction. So first and the foremost thing, it is with respect to the action of NaOH, aqueous NaOH. So basically, what happens whenever you're treating your chlorobenzene, okay, with an aqueous NaOH, remember aqueous NaOH, nearly I am maintaining a temperature of 623 Kelvin temperature and 300 atmosphere. You can just see what is the temperature and what is the pressure I am maintaining. Why is it so? Because it is an haloarene. Its reactivity towards the nucleophilic substitution reaction is very, very less. But also I had to conduct it. So what I had to make, I had to supply more amount of energy and I had to maintain a drastic condition. What it is called as this part, not only this part, high temperature, high pressure, drastic condition. Okay. So of course what I'm going to get is, generally we write it as, you'll be getting your phenol, okay, plus that of your NaCl and the healthy. But do remember guys, what is that? This is not so simple process, whatever we are writing. Of course, in one type we can just write it and finish it off. But what is actually happening is an additional information I'm going to give you. So basically, when you're taking this 623 and 300 atmospheric pressure, of course you're going to get a phenol. But that phenol will not remain as such. So what it will try to do, once again this phenol form is going to react with the excess of NaOH you have taken in the system. So once again it is going to react and it is going to give you sodium phenate. So this is called as what? Sodium phenate. Okay, sodium phenate plus H2O. So this sodium phenate, what it will try to do, the formed sodium phenate, then we are going to treat that formed sodium phenate with respect to that of your HCl, and then you are going to get your phenol plus NaCl. So this is actually what is happening. So when we are treating your chlorobenzene with a NaOH at 623 Kelvin temperature and 300 atmospheric pressure, of course we are going to get a phenol plus NaCl. But that phenol once again reacts with an excess of NaOH which is present in a mixture to give you what? Sodium phenate. The formed sodium phenate, then it will be reacting with that of your used HCl to give you the final product of your phenol plus NaCl. Can you see how does, by maintaining a drastic condition, we are employing our nucleophilic substitution reaction? Of course, such conditions were not observed when we are talking about your haloalkenes. But you can only observe that whenever we are talking about a haloarenes, we have to maintain a very high temperature and the pressure. Now the question arises within the scientist. Is there any possibility by reducing the temperature, or to be more specific, even by at room temperature, can we make our nucleophilic substitution reaction towards the haloarenes? So when such a question strike their mind, of course they came with a conclusion. What is that? Yes, we can do it. But how we can do it was a very much interesting part. and a very much important part. They say that presence of electron withdrawing group, in ortho and para position. They are very much particular about the positions. What they are saying, presence of electron withdrawing group in ortho and para position, yes, increases the reactivity of haloarene, towards the nucleophilic substitution reaction. Now we have to understand how is it. Alva? So yes, we can increase the reactivity of haloarenes towards the nucleophilic substitution reaction. But how? It is only when we are having an electron withdrawing group. Basically, I will give an example. For example, NO2 group, nitrogen dioxide group. So when such NO2 group is present in an ortho and the para position, what happens? Reactivity of the haloarenes towards the nucleophilic substitution reaction increases. So now the question arises. Okay, sir, you said it is with respect to the electron withdrawing group. Can you please explain us how and why only in ortho and para position, alva? Remember, guys, in order to understand this, you have to understand the important major thing. What is that? If a substitution has to undergo, what should be there? Carbon atom should assign a positive charge. I repeat once again. If a nucleophilic substitution reaction has to take place on your haloarene, what should be there? Carbon atom should possess a positive charge. But we came to know what is that? Whenever a carbon atom is possessing a positive charge, it will be highly unstable. So we need something such that the compound should possess a positive charge, but it should not be a phenyl cation. Alva? Such thing should be there. So of course what they did, first they saw, if I'm going to put the electron withdrawing group like your NO2 group in the ortho position, let us see what will be the charge on the carbon atom which will be having your halogen atom. Remember guys, for example, if I'm going to write my like this, ortho substituted chlorobenzene. Yes, ortho substitute. So what I have done, in the ortho position I have given my, what is this? Electron withdrawing group. So what it will try to do, if I'm going to write it correctly in a structured way, I should write it in this way so that it will be easily understandable. NO2 will be having like this structure. So this arrow mark indicates which type of a bond? Coordinate bond. Yes. So now what it will do, of course we know that NO2 is an electron withdrawing group. Why? So whatever the double bond character is there between N and O, oxygen will try to acquire towards it. So what happens in turn? Here now the charge density on the nitrogen decreases. So once, in order to balance that charge, what it will try to do? Yes, it will now take this bond towards itself. So when the bond moves towards the nitrogen, what happens? Of course, this carbon is having the double bond, but this carbon has lost its electron density. So at that moment, this carbon gets a positive charge. Are you able to understand? Once it is getting a positive charge, of course now the easy protocol. OH comes and sit, Cls will be kicked out. We have not formed any phenyl cation, I repeat, alva. We have not formed a phenyl cation. Instead, we have just made the system in such a way that the carbon atom containing the halogen group is bearing the positive charge. So when you treat is this, what you can say, positive charge carbon atom with a nucleophile, easily that OH minus comes and sit over here. Chlorine is a good leaving group. It will be kicked off of the system. Similarly, this was in the case when, see, it was only in the case when you are having in the ortho position. Let us check out in the para position the same way. So here is my Cl. If I am going to write my N double bond O and over here as O. Yes, like this bond I have written. Okay. So now what it will do? This will be taken. So in here now electron density is less. this will be taken. Alva. So when it has done so, what will happen now? So when I am writing this structure, resonance structure, see here, here one bond, here one bond, double bond, N, O. Sorry, here single bond O minus, alva. So what has happened now? Since it has taken over here, now what it will try to do? You should only guide me out, guys. So now the electron density being less, I repeat, since the electron density being less over on this carbon, so now what we'll try to do, this will be provided over here. Since it will come now over here, what happens? Yeah, so now you'll be getting in this way. Carbon atom will be bearing the positive charge. Double bond N, O minus. Yes or no? Can you see? In both the case, we have got as what? The positive center is concentrated on the carbon atom containing our halogen group. When you are treating such compounds as a nucleophile, what happens? See, all these are taking place now. We are not maintaining any conditions for your kind information. Just by the presence of the electron withdrawing groups in the ortho and the para position, it itself is making the system such a way that the carbon atom possessing the halogen group is acquiring a positive charge. Of course, we came to know, okay, whenever electron withdrawing group is present in the ortho and para position, it is making the system in such a way that the carbon containing the halogen group is bearing a positive charge. So one assumption is clear. What is that? Why it is happening so? Now the question arises, why not meta position? I repeat, why not meta position? So when I'm talking about the meta position, of course you can only try with me. Yes, pause the video and try with me. So this is ortho, this is meta, this is para. So my meta position will be where? Yeah, double bond O, like this. Yes, I'm going to write my bond in this way. For that it could be easy for me to signify my bond notations. So now this will be gone over here. So when it has been gone, what happens? Here electron density decreases. So now this will be pulled over here. So once it is pulled over here, what happens? Yes. So the next structure, how can I write? Cl. I can write here plus, here plus band rehna 2. Here you will be having a double bond N. Yes or no? And there you will be having as a O minus and an O. Now you can ask me, okay sir, il plus unto next ten agbotu. Of course this doesn't weight so way. So in order to balance this, now what it will try to do? Sorry, here was the bond alva. Sorry. E bond do. I'm mistaken somewhere. Wait a minute. So now what has happened? Here was a bond, here was a bond, here you has been gone, O minus, and here comes your O. True. Here is your Cl. So now when I am writing this bond, now what has happened? Here I am having the positive charge. So in order to balance this positive charge, what it will try to do? Here now you will be getting your bond shifted. So when there is a bond shifting, what we can write? So now Cl is over here, you can just see. So this bond illi bantu illig bantalva. Illig bantu. Yes or no? Of course here one bond is there with you. Here you are having double bond N, O minus and an O. But since the bond has shifted, bond E double bond E ಮತ್ತೆ E carbon ಜೊತೆ ಇತ್ತು. ಇಲ್ಲಿಗೆ ಶಿಫ್ಟ್ ಆದ ಕೂಡ E carbon ನ double bond ಹಾಗೇನೆ ಉಳ್ಕೊಂತಾರೆ. ಇಲ್ಲೇನಾಯ್ತು? ಇಲ್ಲಿ positive charge ಬರ್ತಾ ಉಂಟು. See, it is not getting the positive charge on this carbon. Instead, it is getting to its adjacent carbon. Alva. So it will not promote the nucleophilic substitution reaction. So that is the reason we are saying. So whenever our nitro group is present in the meta position, it is not going to assign the carbon atom bearing your halogen group. But whenever we are talking about your ortho and the para position, we have seen that the carbon atom bearing the halogen group will be having a positive charge. So that is the reason we say as what? Whenever there is an electron withdrawing groups in an ortho and the para position, that increases the reactivity of our haloarenes towards which one? Nucleophilic substitution reaction. So till now, whatever the explanation we saw, it was with respect to the minus R effect or that of your minus M effect. So that of your resonance effect, we have given the our explanation. That with respect to the ortho and para position, how it does it as assigning a positive charge on the carbon atom. It is not only the case for the explanation. Of course, we can give another explanation with respect to the carbanion formed. With respect to what? Carbanion formed during the system. So before understanding the system, you have to understand some important protocols or important things with respect to this carbanion. So basically, when I talk about a carbocation stability, can you please say which carbocation is more stable when compared to primary, secondary and tertiary? Of course, alva. First comes our tertiary carbocation, which is highly stable. Then we are having which one? The secondary carbocation. Yes. And then we will be having our primary carbocation. Alva. Yes or no? Highly stable is our tertiary carbocation. If I ask what is the reason? Of course, in order to balance this positive charge, we are having what? 3 donor groups. All the 3 methyl groups are the electron donating groups, so easily it can balance that positive charge. In the same way, when I talk about my carbanion, what I am saying, first will be having your carbanion, which is primary. So primary carbanion is highly stable, and then will be your secondary carbanion. Yes or no? And then will be our tertiary first we'll be having our primary carbanion, then we'll be having our secondary carbanion, and then we'll be having our least will be our tertiary carbanion. Of course, why is it so? Yes, why is this? Because as we know that your carbanion, the carbon atom will having a negative charge, and on top of that, when 3 electron donating groups are present, what happens? Electron repulsion takes place. So when such electron repulsion is very high, what happens to stability? Of course, stability decreases. That is the case. But what is the important funda we have to remember here is, if I have any means to take out this charge, what happens to the stability? It is going to increase. Alva. If the same carbanion is having some electron withdrawing group, carbanion ಮೇಲೆ negative charge ಉಂಟು, ಈ negative charge ಒಂದು electron withdrawing group ತಗೊಂತಾ ಉಂಟು, ಅರ್ಥ ಏನಾಗುತ್ತೆ? Stability increase ಆಗುತ್ತೆ. So utilizing now this concept, we are going to understand how can we give us explanation for the nucleophilic substitution reaction of a chlorobenzene using the explanation of your carbanion. So basically guys, when we are talking about an ortho substituted chlorobenzene, that is, you are having your Cl over here and that of your N double bond O, and here you are having your oxygen. So what happens? Let me talk. Here is my OH minus. So see, first of course now this is in the ortho position, it is going to take. So now here I am going to write it in this way in order to show my carbanionic part. Of course now electron density has been decreased, so OH minus goes and attacks on this carbon. So what I'm going to get, yes, so I would be writing my product is in somewhat in this way, OH, Cl. Next, so here I am having my carbanion, which is also attached to an electron withdrawing group, alva. So like this, and here will be my part. So when I'm talking about its resonance structures, of course you're going to get a much resonance structure. But important concept is what you have to keep in your mind. What is that? If a carbon atom containing the nitro group or electron withdrawing group, yes, acquires a negative charge, it can be extended to electron withdrawing group, yes, which increases the stability of the ion, increases the stability of the ion. So what it is saying, you have to understand. This is an important note you have to keep in your mind. It is not going to change. So whenever a carbon atom containing an electron withdrawing group is having a negative charge, remember, it can be extended to the electron withdrawing group. So when it is doing such a thing, that is a negative sign, the electron withdrawing group it can give to that group. So when it is doing so, what happens? It will be going to increase the stability of your ion. Let us see. How is it so? So basically, if I am going to write the structure once again, I am going to write as OH, Cl, as here what I have written. So here I am having a negative sign. Here we are having N, double bond O, yeah, O. So I am having 1 pi electron, 1 pi. So same as what I have written. So what it is doing, since the carbon atom possessing the electron withdrawing group is having a negative charge, it could be given, it could be given to that electron withdrawing group. How it will try to give? Yes. So by this way, you will be getting your OH. Here you will be getting your Cl. Yes or no? Then here you will be getting your double bond. Now this has been gone over here since it has been taken. So double bond NO minus coordinate bond with a nitrogen with oxygen. So since it is donating that negative charge towards that of electron group, electron withdrawing group, what happens? Stability of the ion increases. This was possible when your electron withdrawing group is present in the ortho position. So when I talk the same thing with respect to the para position, how can I write it? Yes. So here I will be having my N double bond O, here O, here I will be having my Cl. Yes. So now OH minus. So what it will try to do, this will going to take by this carbon. Yes. So in turn, in order to balance that, what it will try to do, now this would be coming over here. Since now electron density has been decreased, this is going over here. Just to pay attention in order to show my carbon ion. Resonance effect bardaga na yav tara barde direct agi nanu nitrogen kadege kaliಸಿಕೊಡ್ತಾ ಇದ್ದೆ. ಡೈರೆಕ್ಟ್ ಆಗಿ ಡಬಲ್ ಬಾಂಡ್ ಕ್ಯಾರೆಕ್ಟರ್ ನ ಬರೀತಾ ಇದ್ದೆ. ಯಾಕೆ? ಅಲ್ಲಿ ನಂಗೆ ರೆಸೊನೆನ್ಸ್ ಎಫೆಕ್ಟ್ ಮೆಕ್ಯಾನಿಸಮ್ ತೋರಿಸಬೇಕಿತ್ತು. ಆದ್ರೆ ಕಾರ್ಬನ್ ಬರೆಯೋತಿಗೆ ನಾ ಯಾವ ತರ ಬರೀತಿದ್ದೀನಿ, ಶಿಫ್ಟಿಂಗ್. ಐ ಆಮ್ ಶಿಫ್ಟಿಂಗ್ ದಿ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಟುವರ್ಡ್ಸ್ ಫಸ್ಟ್ carbon atom so that I should indicate the negative charge. So when I am writing it, how you are going to get? So you will be going to get as what? Yes, N double bond O and then O C. Now this will be having the negative charge. Here you will be getting your bonds, respective bonds. Here your OH and a Cl. So when I am writing in the para position also, what I am observing, the carbon atom containing the electron withdrawing group bears a negative charge. So when it is bearing such a negative charge, it could be easily extended or given to that of the electron donating group, which in turn increases the stability of the ion. When such increase in stability of the ion is seen, what happens to the reactivity? Of course, the reactivity also increases. But can you please now say me what happens with respect to the metachloronitrobenzene? Metachloronitrobenzene. So meta positionally very big, N double bond O and a O, alva. So here, here and here. Then I need a Cl. So there is an incoming nucleophile over here. So how the bond is going to shift? Let us see first. So see, like this it is coming over here. Now this carbon ka pi electrons is going to shift over here. So can you see where is the carbon ion is formed? Yes. To the carbon which is adjacent to the carbon which is containing your electron withdrawing group. So now here you will be getting and here you will be getting here OH and a Cl. Still now in the ortho and the para position, what we saw, the carbon ion was associated with the carbon which was connected to that of your electron withdrawing group. But when we are considering with respect to the meta position, what we are observing, yes, the carbon ion is present at the adjacent side of that of your carbon atom containing the electron withdrawing group. So ಆತರ ಇದ್ದಾಗ ಏನಾಗುತ್ತೆ? Of course the stability of those carbon ions will be decreasing, alva. So when the stability decreases, what happens? Reactivity of the haloarenes, meta substituted haloarenes, decreases towards your nucleophilic substitution reaction. So if I'm going to write the final product, that is for my ortho and the para position, alwa illi nodbodu. So illi OH ಮತ್ತೆ Cl2 untalla hege OH ಆಗುತ್ತೆ ಅಂತ ಕೇಳಿದ್ರೆ, remember what happens. I'm just going to show you. So basically you will be having your OH, you will be having your Cl, bond shift agi negative charge ಈ ಕಡೆ ಬರುತ್ತೆ. So you'll be getting a N double bond O, single bond, so coordinated bond with oxygen. Yes, in this way. So now what will happen? Since Cl is a good leaving group, it will move out and this extra pair of electron will form a pi bond. So the final product you will be getting in this way. OH at the and nitro position in the ortho group. Can you see? So this will be my final product. So what we are saying through all these conditions is that whenever, of course we came to know as what, whenever an electron withdrawing group is present in an haloarenes, of course the reactivity towards the nucleophilic substitution reaction increases. That is the first important thing. Second most important thing what we came to know, of course substitution anta bandaga benzene mele we are having three important types: ortho substituted, meta substituted and para substituted. So there we came to know that whenever it is present in the ortho and the para position, that is your electron withdrawing groups are present in the ortho and that of your para position, then only we can say what your haloarenes reactivity increases towards our nucleophilic substitution reaction. And we have seen when we were doing with respect to the resonance effect, we came to know as what, the carbon atom containing the halogen group will be assigned a positive charge whenever an electron withdrawing groups are present in the ortho and the para position. But that is not the scenario with respect to that of your meta position. Similarly, when we studied with respect to the carbon ions formed, what did we see? Yes, whenever in the ortho and para position electron withdrawing groups are present, the carbon atom bearing the electron withdrawing group will be assigned a negative charge, that is a carbon ion. So it can be easily extended to that of your electron withdrawing group, which is going to increase the stability of ion. So this is observed only when the electron withdrawing groups are present in the ortho as well as the para position. In case of the meta position, it is not the case. So that is the reason what we came to know through this video is what, compared to haloalkanes and haloarenes, haloalkanes reactivity, I repeat, haloalkanes reactivity towards the nucleophilic substitution reaction is very high. When compared to the haloarenes, we came to know as what, ortho and para substituted reactivity towards the nucleophilic substitution reaction is very high. One important note, remember, with increase in the electron withdrawing groups, in ortho and para position, reactivity towards nucleophilic substitution reaction increases. Nucleophilic substitution reaction increases. I will just give you an important example over here. For example, if I am going to take my 2,4,6 trinitrochlorobenzene, NO2 and then NO2. Of course, what we know is whenever we are talking about an haloarenes, if we want to make an nucleophilic substitution reaction, I have to maintain a drastic condition, very high temperature and the pressure. But when we are talking about this compound, do remember, just by using the warm water, somewhat warm water, what I am doing is I can easily make it as a nucleophilic substitution reaction. I am going to get as this product, which is nucleophile has been substituted. This is called as a picric acid. What it is called as? Picric acid. 2,4,6 trinitrophenol. 2,4,6 trinitrophenol. Why is it so? What they have said in the important note, with the increase in the electron withdrawing groups, only not that much. Again they say, what is that? In the ortho and the para position, the reactivity of your haloarenes increases towards that of your nucleophilic substitution reaction. That is what we have observed over here. So when we were talking with respect to just chlorobenzene, converting chlorobenzene to phenol, what did we see? We have to maintain a temperature of nearly 623 Kelvin temperature in 300 atmosphere. Alva. But when the same scenario we have taken when we are having a tri electron withdrawing groups that also in ortho and para position, no condition itself is required. Just by utilizing certain amount of heat, we are easily making it as a nucleophilic substitution reaction. Why is it so? We came to know whenever electron withdrawing groups are present in the ortho and para position, the reactivity increases. Further, if you want to increase the reactivity, what we have to do? We have to increase the number of the electron withdrawing groups. Why? What is happening? When we are increasing, what happens? At a faster rate, the carbon atom will be assigned a positive charge. ಎಷ್ಟು ಬೇಗ ಕಾರ್ಬನ್ ಆಟಮ್ ಮೇಲೆ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಬರುತ್ತೋ ಅಷ್ಟು ಬೇಗ ನ್ಯೂಕ್ಲಿಯೋಫೈಲ್ ಬಂದು ಕೂರುತ್ತೆ. ಸೊ ಎಷ್ಟು ಬೇಗ ಆಗುತ್ತೋ ಅಷ್ಟು ರಿಯಾಕ್ಟಿವಿಟಿ ಕೂಡ ಬೇಗ ಇರುತ್ತೆ. So why I am saying this? Because if now you have been given with a question, I have given you first one question ಕೊಟ್ಟಿದೆ. Yeah, CH3Cl chlorobenzene ಉಂಟು. Then you have been given with, for example, NO2Cl, and you have been given with NO2Cl, and you also been given with 2,4,6 trinitrophenol. So now what you can see, question is same, don't go with this answer now. Question is same. What is that? Arrange the following in the increasing order of the reactivity towards the nucleophilic substitution reaction. What first important thing? Okay, these are all haloarenes, this is our haloalkanes. Compared to haloalkanes and haloarenes, haloalkanes will be having the higher reactivity. Okay, that should be coming at the last. But now when you are comparing with respect to the haloarenes part, of course here there is no electron withdrawing group, so it will be having the least reactivity. So first yaad barbeku, least reactive barabeku. So I will be writing which one, that one? Yes, just my chlorobenzene, which will be very least. Soon after that one, which one will there? Yes, the meta position one. Alva, the meta position will be having somewhat higher. So here you will be having your Cl, here you will be having our NO2 group. Then soon after the meta, which one we can write? Yes, this part, para position. NO2 group. Very good, Alva. Then I can write the highest for which one? My 2,4,6 trinitrochlorobenzene. Good to see. But highest will be our haloalkanes. Alva, CH3C. So in order to understand this, today whatever we have learned is very much important.